Without a doubt, one of the most confused principles of dynamic compressor design in my professional experience has been that of fluid head. I have found that understanding this concept can best be achieved by recognizing fluid head as the energy required to achieve specific process requirements. Head is the energy in foot-pounds force required to compress and deliver 1 pound of a given fluid from one energy level to another. One of the confusing things about this concept is that the industry persists in defining head in feet. Head should be expressed in foot-pounds force per pound mass, or British thermal units per pound. A British thermal unit per pound of fluid is equal to exactly 778 foot-pounds force per pound mass of that fluid. Remember, when we deal with fluid head, a fluid can be either a liquid or a gas, depending upon the conditions of the fluid at that time. Ethylene, for instance, can be either a liquid or a gas, depending on its pressure and temperature. If it is a liquid, then an ethylene pump, as depicted here, will be used, and the energy required to increase the pressure of the liquid from P1 to P2 will be defined as head in foot-pound force per pound mass of ethylene. Conversely, if the conditions render it a vapor, then an ethylene compressor, as the one depicted here, would be used to achieve the same purpose. We will see in this section that the amount of energy required to compress a liquid or a gas the same amount will be significantly higher in favor of the gas because the gas is at a much lower density than that of a liquid. Understanding a Mollier diagram is an important aid to understanding the concept of fluid head. Every fluid can have a Mollier diagram drawing. Take a look at this drawing here. It is the Mollier diagram for propane, C3H8. Here, the energy is expressed on the x-axis and the pressure on the y-axis. Increasing the pressure of a vapor will result in increased energy required. Now, having defined the concept of head as that of energy, we will then investigate the different types of ideal gas heads, namely isothermal, isentropic or adiabatic, and polytropic. All of these types of fluid head simply describe the path that the gas takes in being compressed. Finally, in this section, we will cover the definition of each type of head. We will show the assumptions for various kinds of heads and the relative difference in their values. The head required by any fluid compression process is the energy in foot-pounds required to compress and deliver 1 pound of a given fluid from one energy level to another, as depicted in this simplified figure. In any compression process, the amount of energy required to compress 1 pound of mass of a specific gas at a given temperature from the compressor suction flange P1 to the compressor discharge flange P2 is defined as head required. The next figures I'm going to show you demonstrate how the density of a fluid significantly affects the amount of energy or head required in a compression process. In the case of a liquid like water with a density of 62.4 pounds per cubic feet, it requires only 231 feet-pound force per pound mass of water, or simply stated 231 feet of head to compress the water 100 psi. The general equation for head required by a liquid is seen here. Notice how it is independent of temperature. So the head of the liquid is expressed in feet and is equal to 2.31 times P, the pressure, expressed in psi, and the pressure here is the absolute pressure, divided by SPGR, which is the specific gravity of the fluid. Now, in the case of a gas, like for nitrogen, with a density of 0.07 pounds per cubic feet, it requires roughly 350 times the energy required by water. This is because in both the case of water and nitrogen, the process requires that the fluid be compressed 100 psi. However, since the mass of nitrogen is only 0.1% of the mass of water, a much greater amount of energy is required to compress the gas. The equation for head required by a gas is seen here. We'll get back to it further ahead. Now, the following figure shows, for a reminder, the head-produced characteristics of positive displacement and dynamic compressors. Note that regardless the amount of head required by the process, the flow rate of a positive displacement compressor is not affected. On the other hand, a dynamic compressor's flow rate is significantly affected by changes in the head required by the process. This is because the characteristic of any dynamic compressor is that it can only produce a greater amount of energy at a lower flow rate. The reason for this will be explained further ahead. Therefore, any increase in the head required by a process will reduce the flow rate of a dynamic compressor. This is an extremely important fact to remember because reduced flow rate in a dynamic compressor can lead to extreme, long-term mechanical damage to the compressor unit. Also note in the figure corresponding to the dynamic compressor that the flatter the head-produced curve for this compressor, the greater the effect of head required upon flow rate. A strong understanding of the concepts of head required by the process and head produced by the compressor is absolutely essential if you want to understand dynamic compressor operation. It has been my experience that a lack of understanding exists in the area of dynamic compressor performance and often leads to a much greater emphasis upon the compressor's mechanical components, like the impellers, the labyrinths, the seals, the bearings, and the shafts. In many cases, the root cause of dynamic compressor mechanical damage is that the head required by the process system exceeded the capability of the dynamic compressor. Now, the factors that determine the head required by the process are the following: the system resistance, defined by the ratio discharge pressure divided by the section pressure, or P2 divided by P1 in this course, the gas composition, namely the molecular weight, the compressibility, and the heat ratio. There will be more about this in a later section. And finally, the last factor is the inlet temperature. What I want you to remember and understand for now is that the head required by the process increases if the system resistance increases, so if the ratio P2 divided by P1 increases, or when the molecular weight decreases, or when the temperature increases. And that, on the other hand, the head required by the process will decrease if the ratio P2 over P1 decreases, or if the molecular weight of the gas increases, or if the temperature decreases. Note here that the head required by the process is inversely proportional to the gas density. If the gas density decreases, the head required by the process will increase. Gas density will decrease if gas temperature increases, inlet pressure decreases, or molecular weight decreases. If the head required by the process increases, the flow rate of any dynamic compressor will decrease. This is, if you recall, was discussed in a previous video and is illustrated here again with the following figure. Notice here that if the head required by the process increases as from 1 to 3, the flow rate of the dynamic compressor will decrease. So please keep in mind that if the gas density increases, the head required by the process will decrease, and of course the dynamic compressor flow rate will increase. Simply stated, for a given impeller vane shape, head produced by a dynamic compressor is a function of impeller diameter and impeller speed. Once the impeller is designed, it will produce only one value of head for a given shaft speed and flow rate. So the head produced by the compressor will increase if the diameter of the impeller increases, or the speed of the compressor increases, or if the flow of the compressor decreases. Now take a look at the following head capacity curve for a centrifugal compressor working at different speeds. For a given flow, let's say here, and a given speed, let's say 90%, if an operating test point does not fall on the curve as seen here, then your unit requires maintenance. The only factor that will cause a lower value of head to be produced than stated by the compressor performance curve is if the compressor has experienced mechanical damage or if it is fouled. The following pictures will show a case of a fouled compressor that we have experienced recently at our plant. You can see here the impeller severely fouled with dust and fines that were carried out with the process gas following a dysfunction in one of the filters upstream the compressor. Here the same impeller is seen from a different angle. And here a closer look at the impeller to show the impeller labyrinth seal, highlighted here in yellow. We'll cover them later on with more details. And finally, a picture showing the rotor, that is, the impeller on one side and the rotating shaft with the bearing and mechanical seal mounted onto it on the other side. Now let's go back to our head capacity curve for a centrifugal compressor running at different speeds. What I want you to understand and to remember here is the following important fact. So, if for a given flow rate, let's say here, and a given shaft speed, let's say 90%, if the head produced, as you can see here, falls below the value predicted by greater than 10%, then your compressor should be inspected at the first opportunity. Now that we have explained the concept of head required by the process and the concept of head produced by the centrifugal compressor, it is time to take a look at the method of calculating the head required by a process system needs. This will be the topic of the next video. This figure presents a typical Mollier diagram plotted pressure versus energy. A Mollier diagram can be drawn for any pure fluid or fluid mixture. Usually, Mollier diagrams are prepared only for pure fluids, since any change in fluid mixture will require a new Mollier diagram to be prepared. The Mollier diagram can be used to determine the head required by the process system for any liquid, saturated vapor, or vapor compression process. Observe in our case here that for liquid compression, the amount of energy required to increase the pressure from P1 to P2 is very small. However, for compression of a vapor or a gas, the amount of energy required to compress from P1 to P2 is very large, and this for all types of compression: isothermal, isentropic, polytropic, or axial or wheel compression. This is because for a given compound, its mass is lower in the gas state than in the liquid state, and therefore a much greater amount of energy is required to compress the gas the same amount than the liquid. You can refer back to a previous video of this section and study the equations that were used to determine the head required for a liquid and a gas. In addition to many more parameters being needed for calculation of head required for a vapor or a gas, certain ideal assumptions must be made. We'll introduce them in the next couple of videos. A gas can be ideally compressed by any one of the following reversible thermodynamic paths: isothermal, where the temperature remains constant; isentropic or adiabatic, where there is no heat loss during the compression process; and finally polytropic, where temperature is not constant and heat is lost during the compression. The actual path that any compressor follows in compressing a gas is equal to the reversible path divided by the compressor's corresponding path efficiency. Therefore, we can write the following equation. So, the actual head is equal to the isothermal head divided by the isothermal efficiency, which is equal to the isentropic head divided by the isentropic efficiency. And likewise, it is equal to the polytropic head divided by the polytropic efficiency. The point here is that when evaluating compressor beds for different vendors, quoting different types of reversible heads, then this equation proves useful. If the head produced by one vendor divided by the corresponding efficiency is not equal to the corresponding values quoted by the competition, then better start asking why. The following figure shows different types of ideal heads and the relative difference between their values as compared to polytropic head. Recall that for isothermal head, the temperature of the gas is constant during compression, and that for isentropic or adiabatic head, no heat is transferred during compression. And finally, that polytropic head most closely approximates the actual compression path. I'm aware that at this moment, the definition of polytropic head is confusing and difficult to understand if not investigated further. For this reason, we'll get back to it later on. But for now, let's first take a closer look at the different ideal gas head equations. The first head equation that we will see is for the isothermal compression. Then the isentropic or adiabatic, and then polytropic equation. In these equations, mW is the molecular weight of the gas being compressed, Z its compressibility factor, T1 is the inlet temperature, P1 is the suction pressure, P2 the discharge pressure, K is the ratio of specific heats, so Cp divided by Cv, and N is the polytropic exponent. Note here that the only difference between isentropic and polytropic head is the values K divided by K minus 1 and N divided by N minus 1. Also note that these two values are related by the following formula. N minus 1 divided by N is equal to K minus 1 divided by K divided by the polytropic efficiency. So now if the polytropic efficiency is equal to 100%, then N minus 1 divided by N is equal to K minus 1 divided by K. Or stated otherwise, the polytropic head is equal to the isentropic head. So, having said that, I personally think of n minus 1 divided by n as a correction factor to K minus 1 divided by K, and this factor will most closely approximate the actual compressor path for a given compressor. Remember, polytropic head is an ideal reversible compression path. Today, most compressor vendors have adopted polytropic head as their standard for multi-stage compressors. The main reason for this is that polytropic head, since it contains an efficiency term, allows individual impeller heads to be added. There will be more about this in a later section. To finish off this section, let's take a look at the following figure. It presents the different ways that compressor performance curves can be formatted. So, head versus flow, or pressure ratio versus flow, or discharge pressure expressed in absolute PSI versus flow. The curves that you can see here represents the head generated by the dynamic compressor, and the one that you can see here represent the resistance of the system. In the industry, head versus flow is always preferred because the head produced by a dynamic compressor is not significantly affected by gas density. However, compression ratio or discharge pressure are. That is, compression ratio and discharge pressure curves are invalid if the inlet gas temperature, inlet pressure or molecular weight changes. This may be confusing at first, but refer back to a previous video where we talk about how head is produced by a dynamic compressor. Recall, it is a function only of impeller diameter and shaft speed. Gas density has an impact on the head required by the process only.